Just to start off, maybe just to orient the audience, do you mind introducing how bioelectricity, bioelectrical states, ended up playing a role in developmental biology to sort of change the conventional wisdom of how gene expression determines everything?
Yeah. Well, I mean, one thing to keep in mind is that I'm certainly not saying that gene expression is not important. Absolutely, it's a required component of this, and so there are kind of three streams of three main streams that are really critical to setting up any kind of patterning, which is biochemical signaling, including gene regulatory networks and transcription, and then there's biomechanical signaling, and then there's bioelectricity. So all of these three things are important, and they all sort of interplay back and forth to implement this cooperativity among cells to build the body and various parts of it. The interesting thing about bioelectricity is that, much like in the brain, it plays, I think, a rather unique role, although it's possible that someday people will find that some of the other modalities do it too. Uh, I think evolution really likes to use bioelectricity as a computational medium. So if you think about what happens in the brain, I mean, a lot of this can be actually nicely visualized by thinking about the brain and then loosening some constraints. So we think about what happens in the brain. You have an electrical network, and this electrical network allows very rapid learning, decision making, memory, preferences, goals, these kinds of cognitive things. And then the electric circuits have their say, and then this gets transduced into neurotransmitter movement, other second messenger cascades, and eventually changes in gene expression in the brain. But these are all, sort of slower downstream steps where a lot of the initial computation is done at the electrical level, right? So the rest of the body is basically very similar, and that's not an accident. It's because I think that these bioelectrical dynamics were the evolutionary precursor of what we see in brains and neurons. So I think what evolution did was basically speed optimize these dynamics that had always been going on since the time of bacterial biofilms. So I think if you zoom in on a single cell level, what you see is electrical properties that become transduced through one of half a dozen. We know about half a dozen transduction mechanisms. They become transduced into changes of cell behavior, including transcription changes, including cell motility, cell shape, apoptosis in some cases, proliferation, all these things. So that's if you zoom in at the single cell level. If you take a step back and ask what is the bioelectrical layer doing? Well, it seems to be doing a number of computations that have to do with making decisions at the tissue and organ level. So it decides things like, if you're a regenerating planarian, how many heads should we have? If you're a developing frog face, where do the eyes go? How many eyes? Where does the mouth go? Right? Those kind of decisions. So that's our goal is not only to understand the molecular details of transduction at the single cell level, but to take a step back and crack the code on a tissue and organ scale, and to say, how is it that specific bioelectrical pre-patterns map onto changes of gene expression and anatomy that follow them.
Right. Was this a surprise to you? Because I mean, in a way, this has to have always been around. They're far older than human brains, but is it a surprise to you how successful the research has been and how far it's developed?
In the details, absolutely. So I'm always stunned when I see new examples of bioelectric pre-patterns, when we develop new control modalities where we can make something new phenotypes, and we can make something cool happen or repair a defect. That to me is the most amazing. As so those things kind of surprise and shock me every day. On the other hand, I started down this road. Basically, my first thoughts about this kind of stuff was when I was probably 17, coming across Becker's Body Electric book and starting to think about whether these things were not just another piece of physics, but actually the information carriers that might have been what the medium by which the body processed information before brains and neurons. Like that's something that's something I've been thinking about for many years. And so from that perspective, it's kind of it didn't really fall out of the blue, because I've been sort of working toward this. But I'm shocked every day when I see these things actually working. It's just, it's amazing.
Right. One of the most insightful points that I take away from your work is how bioelectrical mechanisms aren't novel to the brain.
Yeah, right. I mean, it's interesting in a couple of ways. On the one hand, certainly uh, there's a lot of focus on, for example, if you on in neuroscience, of course, on neurons and on spiking and so on. But people who study fertilization, physiology of kidney, inner ear, of a gut, these kinds of things. I mean, those folks have been studying electrical circuits for a long time, and of course, there's a whole literature on developmental bioelectricity going back. I mean, some of the first experiments are in the early 1900s, and then there was a kind of a wave of research in the 30s and 40s, and then again in the 60s through the 80s, and a lot of it got sort of deprioritized when molecular genetics came on the scene because doing biochemistry is easier because you can work with dead cells and tissues. You can right grind them up and extract the DNA and protein. This stuff is hard. This bioelectricity you can only see in the living state. So so a lot of that information has been around, but you can also sort of reach a lot of this from first principles if you just ask yourself, well, where did neurons come from, right? And now we're starting to see that all the machinery, ion channels and synaptic machinery and neurotransmitters and all this, they're ancient, and they were even in the kind of in our unicellular ancestor already had a lot of this stuff, right? So you can sort of then naturally start to ask the question, okay, so and by the way, some very beautiful work in bacterial biofilms now from Grohl Swell's lab. So yeah, if you just sort of ask yourself, what are the evolutionary precursors of the kinds of tricks that the brain is able to do? Then it becomes kind of natural to think about it.
Right, right. I read something about how you found different types of memory in just gene regulatory networks, um, which was very surprising.
Yeah, this is a different kind of line of research for us because it's not bioelectric in any way, but the majority of our lab, in fact, the kind of the central theme of our lab is looking at cognition in unfamiliar guises. So we're interested in understanding different aspects of mind, of intelligence, of problem solving, and in all kinds of weird implementations, right? So bioelectricity is great because it really helps understand the story of how individual competent cells work together to be a higher level agent that solves different problems in morphological space, for example, instead of cellular or physiology space. But there are other architectures that do this too, and gene regulatory networks, of course, are very popular in terms of in standard developmental biology and so on. And what they illustrate now, but also we are not the first person, we are not the first to realize that gene regulatory networks can learn. So Richard Watson and a few other people have had papers on this for a long time. What they help us see is the kind of uh, folly of making assumptions about levels of agency of something before you check it. So if you look at a gene regulatory network model, you would say, okay, look, this looks just like a piece of chemistry. I can see everything that's happening here. There's no magic with this. This thing is going to be basically at the level of a mechanical clock, right? That it's a deterministic piece of physics, and that has medical implications. It means that if I want to change how this works, I have to manipulate the hardware. I have to remove nodes, add nodes, change promoters, add new genes, and so on. I have to change the topology of the network. So, but that's a really limiting assumption, because if you don't sort of assume that zero level of cognitive capacity here, but you actually say, well, let's find out. Let's see what it can do. What you can then discover, and what we did, was to actually probe something like I don't know, 50 or 60 existing biological gene regulatory networks compared with random ones that you just make up for controls. And you simply ask the question, can they learn from prior experience? And the GRN experience means a stimulation of one or more of the nodes. And so having had that experience, what do they do later? And what we found is that we can actually make a taxonomy of 6 different kinds of learning, including habituation, sensitization, and remarkably associative learning. And we found that even GRNs are capable of, if you look at them the right way, meaning if you choose the right nodes for your stimulus, your conditional stimulus, your unconditional stimulus in your response, if you look at them the right way, you discover that, yeah, they can do associative learning. It's amazing. Right. And so that it tells you 2 things. It tells you, number one, to be really careful when making assumptions, because some things are smarter than you think they might be. And so it's an empirical question. You have to check. You can't just sort of assume or have feelings about it. That's the first thing. And the second thing is it gives you a really interesting new way to think about how to use drugs, because this idea, right, that you find a dose and you put the patient on that dose and then you sort of stay there and hope for the best. That's in many cases that's not going to be the best way to control the pathway. The better way would be a timed pulse stimulation where you're literally trying to uh, behavior shape it's behavior shaping, it's not rewiring at that point. So that's a completely different way, and we're certainly working now on those kinds of applications.
Right. So, like thinking about the foundations of cognition, bioelectricity or gene regulatory networks are widely used because we have the understanding, the work is set out, and we have the technology and tools to intervene there. But in principle, they're not privileged levels of substrate. There's no such thing as a privileged substrate. It's just what's convenient given the reality of it. Is that sort of
Yeah,
right?
I think you're right. I think there's two levels of convenience here. There's what's convenient for us as scientists, in that there's an old saying, I don't know who said it, but the show me the net that you're using to fish, and I'll tell you what fish you can find, right? So they're convenient for us, meaning yes, we found them. Who knows what else we're not finding, because it's not convenient. It's an alien form of cognition that we're just not good at noticing. It keeps us humble. It should keep us humble about that. Um, the other thing, though, is that clearly evolution finds it very convenient. So, for example, bioelectrics is an amazingly convenient interface that cells and tissues expose to whom? To us as engineers, but also to evolution itself, to each other, to other cells, and also to parasites and conspecifics and various other things that might exploit them. But you're right in that I don't think there's anything magical about either bioelectrics or GRNs. They're just the examples we understand now, and it's entirely possible that, for example, there's a few people that have done some amazing work on networks of springs, and literally just springs, and so Christopher Buckley and Richard Watson have been studying various kinds of learning and behavior in networks made of springs. And for all we know, there are other architectures that exploit biomechanics, magnetics, optical phenomena. Who knows, right? In the wide universe, I mean, there's probably many other substrates.
Right. So there might be like principled limits as to how far we can look at the substrates, like Gödelian type of limits, as we can only scale up to a certain extent just because we might have some epistemic machinery that stops us from going further.
Yeah, it's entirely possible. I mean, it's the problem of giving an IQ test to somebody who's smarter than you, right? It may be really hard, right? It might be really hard for us to recognize new kinds of intelligence. It's related to the problem of hierarchical nested intelligence, which I'm also really interested in. You know, individual cells work together to form larger agents that solve larger problems. They form tissues and organs, and individuals form collectives and ant colonies and things like that. One might ask, as an individual, can you tell if you are part of a larger system like that? And if you can, what might the goals of that system be? Now, I think you're right in that there are probably serious Gödel type limits as far as really being if you're really just a piece of the machine to really understand what the collective is doing. We probably cannot understand that, but you might be able to gather evidence that something like that is going on, right? If your action space is being distorted, you might be able to gain evidence that it's not being randomly distorted. So I like to think about this as a imagine for the moment that you're a neuron in a neural network that's being trained, right? And so if you could, and I know I'm mixing metaphors here, but if you were smart enough to ask the question, you might ask yourself, do I live in a cold mechanical universe that doesn't care what happens to me? Or do I live in some sort of mindful, bigger picture universe where there's a bigger picture and a grand design of some sort, right? So humans argue about this all the time. Some people say, no, we're sort of cogs in a mechanical machine, and other people say, no, life teaches me lessons, and I feel like there's a greater pattern, right? So if you think about that from the perspective of a neuron, if that neuron were to conclude that the universe that it lives in is a sort of a zero agency sort of cold environment, it would be factually wrong. Because in fact, right, because as the network is being trained for certain things, so you could imagine, certainly it can't have a good understanding of what the goal is, but it might, as these waves of back propagation and sort of external tuning of the wash over it, it might realize that, certain things get rewarded and punished in this world. And maybe there is, right, maybe there is some kind of a purpose to what's going on that is different from just randomness. So I don't know, again, I think it's a good, there are certain, I'm sure there are Gödel limits, but we might be able to get at least probabilistic evidence that something is happening to us.